You know.
Has been put together by a variety of different entities. The Madrona Institute really took a leadership role, as did the National Park Service. There's a donation jar in the back for Madrona Institute if you'd like to see more events like this in the islands. They very much appreciate your donations. My name is Linda Leitchell. I'm the Conservation District Manager, and we're one of the co-sponsors for this event. And we are charged with natural resource conservation in the islands, and one of our goals is to help us reduce our energy use and to address climate change through a very proactive and positive manner. So we've launched an energy program. We're working with Opalco and many of our local groups here in the islands, and we're developing a countywide energy plan as well as a community solar project. And there's some literature in the back about our community solar project. There's a brochure that explains it, and there's also a sign-up sheet. If you're interested in finding out more and would like to participate in the community solar project. So have a look at the materials in the back. There's also a wonderful bookmark that was put together by Friends of the San Juans and the Madrona Institute, and it talks about 5 things you can do to address climate change. We also have some energy saving tips in the back and several other wonderful sources of information. So I also wanted to let you know that this is the second in the series. We have several more after tonight's talk, so do come back for the next ones. And we do have some handouts in the back that let you know what all of the different events are. Now I'm going to introduce Fiona Norris. Fiona is the Science Director at the San Juan Nature Institute, and she is going to introduce our speaker for this evening.
Well, thank you, Linda. Welcome. It gives me enormous pleasure to introduce Jan Newton. Last time she was in Friday Harbour, I missed out completely, so I'm very pleased to be able to make it up tonight. She is Principal Oceanographer with the Applied Physics Lab. That's an interesting juxtaposition. And the Applied Physics Lab is allied with the School of Oceanography. That's more realistic, we understand that. And with the School of Marine and Environmental Affairs. So this woman wears 3 hats, but I haven't finished yet. She spent her life looking at the ocean, and from the Hood Canal oxygen problem to the outer ocean. She was, are you still director of NANOOS?
Yes, I am.
I love that. NANOO, it reminds me of my the
Northwest Association
of Ocean Observatory System. This is a magical system which we can tap into and look at real-time data being generated out in the ocean, a whole chain of observatories from here through British Columbia. She was in July 2013. She and Terry Klinger were appointed joint directors of the new Ocean Acidification Lab at UW. And that is a testimony to her research, her lifetime's work, studying the economic, the physical, the chemical, and biological dynamics of our sailor sea and ocean systems. So nobody is better qualified, in my personal opinion, to talk to us about climate change and its effect on the ocean. So welcome, Jan.
Thank you, Fiona. Wow, Fiona, thank you so much. You know, honestly, I was just a kid who grew up on the shores of Puget Sound, and my folks would take us up to the San Juan Islands, and one day we wandered over to the Friday Harbor Labs, and I saw a woman with a clipboard, and my life hasn't been the same since. It's really true. Thank you. So it's really my pleasure to be here. Anytime I can be up in the San Juans, my heart is happy. And any time I can be talking about the oceans, double that. So thank you so much. I am going to do something I've never done before, which is to actually play you a video to begin this talk off. I think that this video says in 4 minutes what I hope to tell you in 40 minutes in a more depth, but it's a wonderful video that you can watch. So bear with me and hope that this works.
In the last 200 years,
that's all we can do.
Rapidly changing a process called ocean acidification. Ocean acidification has the potential to fundamentally change the oceans, its inhabitants, the food webs, and marine life. We need to better understand how acidification affects our oceans so that we can develop tools to slow the rate of change. The U.S. Integrated Ocean Observing System, or IOS, uses real-time data to signal the approach of acidified seawater 1 or 2 days prior to its arrival, providing shellfish farmers with the tools to save their crops.
This is Detarts Bay, Oregon, and we have a shellfish hatchery here. What happens in the oceans really affects what happens to my business. The IOS data helps us to manage our hatchery. We pump in 75 to 100,000 gallons of seawater a day. We've got 20,000-gallon tanks. As we drain tanks, we fill tanks. We never stop filling tanks. It looks like dirt, but what you're looking at is 100 million larvae right here. It's a huge responsibility to try to produce shellfish larvae. What you grow not only affects your business, but families out there depend on this larvae to seed their ground. And if you're not producing, you're affecting their livelihood. So there's a balancing act here. Everything's got to be just right to get these larvae through. We bought a back production in 2008. We would bring the water in, put the larvae in it, and they would die, mysteriously die. In the back of your mind, you're thinking, maybe it doesn't work anymore. Maybe we lost our mojo. My wife said, you gotta throw the book out and I used to grow larvae because it's a new ocean. It's a changing ocean.
I pretty much thought we were going to lose the business. We never had no survival. That was the difference. We had zero survival.
What drives the pH down is the amount of CO2 that's in the water. On a scientific level, they call it acidification. The larvae hated it, they either slowed down their growth or they died. This is where IOS steps in. These guys have the ability to monitor the oceans. This is what helps us run our business, dealing with these changing ocean chemistry.
We used to never treat any water with anything. And now we filter, skim, treat with carbonate, add air and oxygen.
Without the monitoring, we'd be driving 9 to 9, run off the road immediately in the ditch, we'd be out of business. This is not a localized problem. It goes beyond what we're doing right here. Don't make it a party issue or anything like that. We're talking about the ocean. We're talking about something bigger than all this put together.
So the rest is credits. And so I just wanted to play that because, you know, Fabian Cousteau and Mark Weigart, a shellfish grower, can say it more eloquently than I. What I'd like to accomplish in our time together here is give you some of the basic underpinnings of understanding what ocean acidification is, talk to you about why it's important that we work across all scales, local to global. Talk to you about what's going on in Washington and how our former governor and present governor have really taken some leadership. Talk to you about the Washington OA Center that it's my honor to co-direct with Terry Klinger, who many of you probably know, and to give you a glimpse at some of the data that we're learning about. So if you'll pardon me, let me quit this and get to this. All right, now I'm on familiar ground. Okay, so yeah, you know, Fiona gave me a lot of accolades for the associations that I have, but what I've learned over the course of my career is that it takes all these perspectives to really study an issue well. So I've been fortunate that they haven't kicked me out yet. Okay, and here's one thing that I didn't test, and that's the remote, so I'm just gonna improvise. All right, so when I explain ocean acidification, I like to invoke two natural critters or natural items on the planet. One is a volcano and one is an oyster. And so you are actually standing on Mauna Loa looking across at Mauna Kea. And right here is the CO2 sensing lab that's been there for a long time because Charles David Keeling in the early 60s decided that that would be a wonderful place to go start measuring CO2. And he persisted in his fervor to monitor. And for those of you that are involved in gathering measurements, you know how critical it is to sustain that. And that's really our information. And so if we didn't have these data, we wouldn't understand a lot about the CO2. Because as people started to see these changes, they said, wow, maybe we should monitor it other places. And so if we look at this part of the record, so there you can see Mauna Loa on the big island of Hawaii. And you can also see that thing that says Station Aloha. That's just a group of coordinates in the ocean that vessels go to. And so now over here, you know what? I have a.
I'll try to fix that for you. Wait a minute.
Okay.
Let me see if I can get that.
Because I have one that I think might work. A girl never goes anywhere without her magic projector thing.
Yours may work better than mine. It's not working.
Let's try it.
Oh, it's off because it's off.
Oh,
There we go.
there we go. Does it have a laser light?
It does.
It does. All right.
There you go.
Okay.
Sorry about that.
Thank you. No worries. Okay. Oops. All right. Thank you so much. So if we move back to here, this red data series now is this red data series right here. And what you're also looking at is the seawater CO2 trend. So, and that was gathered from this station by folks going out on ship cruises repeatedly. And so you can see this up, down, and that's actually the breathing of our planet. So there's more photosynthesis in the summertime, right? And so that takes up CO2. And then when all those plants die back during the winter time, that doesn't take as much CO2 up. So that's this up, down that you see in that red squiggle. And the fact that it's increasing is because we're adding more and more CO2. But what's really amazing, and we didn't start to learn about until the early 90s, is that the seawater has that exact same signal. The slopes are very much similar. And then this axis down here is pH. And so it has the opposite slope. So we've got air CO2 and seawater CO2 increasing and seawater pH decreasing, all right? And so what's causing that air increase is this. It really is carbon combustion. So whether it's your car or smokestacks or whatever, it's the burning of fossil fuels. That is 90% of the issue. Deforestation is 10% of the issue. Why deforestation? Because you're pulling down trees that photosynthesized, right? So you take down those things that used to take up CO2, and so you don't have as much uptake. This contributes CO2. And so where does that CO2 go? Well, about half of it is in the atmosphere, and that's that rise that you see, which would be even more of a rise if the oceans and the biosphere didn't take it up. So the land plants and then the oceans. So about a quarter of the CO2 that goes into the atmosphere winds up dissolving across that air-sea interface into the ocean. All right, so when you hear about CO2, most people think of the global warming, right? So the increase of CO2 causing that greenhouse effect and causing warmer temperatures or climate change. Well, this is the other effect from the increase of CO2, which is that it winds up in the ocean and has the effect on chemistry. And I'm not going to go through all the chemistry because it's complicated, but also I want to spend time talking about other things. But the CO2 in the water, it creates this thing called carbonic acid, and people get scared right about that. But it immediately dissociates, so don't worry, the ocean's not filling up with acid. But when that carbonic acid dissociates, that increases the hydrogen ion content, which is what pH is about, and pH is an inverse scale, so isn't that easy? Okay, so the pH scale, that's how we measure acidity. And so you know that neutral's right around 7, this is acidic, this is alkaline or basic. Seawater is not acidic, it's not even remotely close to being acidic. It's 8, but when we add that CO2, it drives it in the acidic direction. All right, so 2 things to know about pH is that it's on a log scale, just like the Richter scale, right? And so a 6.0 earthquake's a lot worse than a 7.0. So these differences between like 8.1 or 7.8 are actually big. So small changes in pH units are much larger than changes in acidity. And the other thing is that we call it acidification because it's in that direction. But this is something that always alienates the public when they don't understand the underlying chemistry, because they'll say, seawater's not an acid. What are you bozos telling us? But when you say that, you know, you've got a cold snap and it's 28 degrees Fahrenheit, right? And then it warms up to 33. You say it warmed up, right? Does that mean that 33 is warm? No, it just meant that it went in that direction. This is the same thing. And debasification is just really not a good term. It truly is acidification. It's the power of the hydrogen ion. So it is just true chemistry. All right, so here is the history and future of ocean acidification at the ocean surface. And so here is pH, and of course this is the grand average of the world oceans, zooming along here at about 8.2, and you see that in the year 2000 it had already nosedived, CO2 increase. And so by 2000, that change in pH unit of about 0.1 is actually a 30% increase in the acidity, right? Because it's a log scale, okay? And then there's also this decrease in carbonate. And we haven't talked about carbonate yet, but that's a really critical building block for some organisms. So, okay, so that's disturbing enough. That's 2000. This is where we're headed if business as usual, all right? By the end of the century, 150 to 200% of increase in acidity and a 50% drop in the carbonate ion concentration. So that's a big change. All right, so just to summarize, ocean acidification, CO2 added to seawater changes the water chemistry such that pH is reduced and the carbonate ion availability is reduced. All right, so that's enough from the volcano. Let's hear from the oyster. All right, so here's a picture from Seattle Times back in, I used to remember the date. Anyways, I think this was published in 2006 or something because it's talking about 2005. Anyway, people first started noticing that out in Willapa Bay that the natural set of oysters wasn't happening. So in Willapa Bay, so there's 2 ways you can grow oysters. One is you rely on nature to bring in that little larvae and settle and they grow. The other is you can have a hatchery like you heard of in the video, where they actually grow the larvae. They it's animal husbandry, right? They get the fertilization of the 2 sexes of oysters, and they make the little larvae. They rear them until they're little culch, I guess they call it, and then they send it out to oyster farms. But this was interesting because the natural set wasn't happening. And so people were wondering, could the chemistry be killing the sea life? And so this was kind of a hypothesis floating around. And so let's look at this a little bit more. So we've been talking about that change in pH from adding CO2. But the thing of it is that when you add CO2 to water, it wants that carbonate ion because the equilibrium of that chemistry is that it wants to make bicarbonate ions. And so that's why it takes these away. And this is the building block of calcium carbonate, right? Calcium carbonate. And so there's two different, what they call biominerals of calcium carbonate. Anytime you go out there and you see a nice shell, like clam shell, oyster shell, that's calcium carbonate. Aragonite or calcite. Really cool names. But anyways, so aragonite is the form that the baby oysters lay down first, and then they put down calcite. Aragonite is the most sensitive to a change in pH or an increase in CO2. So we're going to define something called the saturation state of aragonite, which, again, the problem with ocean acidification is that the terminology and the underlying chemistry is something that, you know, believe me, people don't go around talking about aragonite saturation state much. So it gets a little obtuse, but it's really, will this shell stay as a shell, or will it start to dissolve? And so the chemists can measure that. They abbreviate the saturation state by this little Greek letter omega. And so if omega equals 1, that's the equilibrium or threshold. If it's above 1, shell building is relatively easy. If it's below 1, it's going to dissolve, or what people have termed corrosive conditions. Okay? So, and you know, it's not a perfect translation, but aragonite at the threshold is when pH is around 7.7. But of course, as any good chemist knows, that depends on the temperature and the salinity and the pressure, so nothing's ever easy. But here are some experiments that folks down at OSU did. So the man you saw in the film, Mark Weigert and his wife Sue Cudd, they run the Whiskey Creek Oyster Hatchery down there in Oregon. And they started noticing problems, as you heard about. And so OSU is near there. They have a marine lab near there. And so they started working with folks like Burke Hales and a student named Alan Barton, who was getting his master with Burke, and then started working for the hatchery. And they decided that, hey, we got to investigate this. So this is omega aragonite in seawater. These are different measures of growth, all right? So this is the production, how much larvae get produced, and this is the growth when they're actually feeding. And you can see that there's a linear relationship, that the higher that omega is, the happier they are, the more they're producing, the more they're feeding, and the lower it gets, the less of that. But I always think a picture is worth 1,000 words. So here are little oyster larvae. They call it the D-hinge stage for obvious reasons. And so here's when aragonite is 1.6. And these two are when aragonite is basically 0.5. And so you can just look at those and see which ones are healthy and more likely to grow into the oysters that we would like to eat. So, just summarizing, what do we know? We know with certainty that atmospheric CO2 has increased from human activity. The amount of the increase is equal to the amount of fossil fuel burning. We know that the oceans absorb CO2. Those data sets show us that. We know the increased CO2 causes ocean acidification. It's basic chemistry. It has these two effects on the pH and the carbonate levels, and we know that OA reduces growth and survivorship in some organisms, and we'll talk about other organisms too. So those are things that we know, and the IPCC, the Intergovernmental Panel on Climate Change, has written about, and so there's that. But the thing that I find most scary about this whole issue is the rate at which it's happening. Any good citizen of the planet knows that change is inevitable, right? We don't live in steady state. Things are always changing. We know we've had glacier epochs and all of that. We know that there's been a lot of change and that change is going to go on. But the rate of that change dictates how well you adapt, right? I mean, if something happens really quickly, you're scrambling. But if it's more protracted, you can adapt. Well, The rate of change in the CO2 concentration has no parallel in 300 million years, and so that's what's concerning about this whole issue is that as we would like to see biological adaptation, we're really pushing this system. We really are pushing this system. So what are the implications for food webs and ecosystem services? Well, largely we don't know. A lot of study is going on, but there are some things that are being known more. So one of them is this beautiful organism here. It's a pteropod, Pteropods. Once again, I mean, ocean acidification, you got Aragonite, you got pteropods. It's like, what are you talking about? I mean, these are not common words, but let's call it a sea butterfly because these little wings right here actually beat up and down much like a butterfly wings. And so there are a lot of pteropods. In fact, if you took a net haul, you know, you could maybe be lucky and find some pteropods here. They're very plentiful out in the open ocean. And so they're a type of plankton, and salmon can eat them, other organisms can eat them, they're part of the food web. But this little part right here is a beautiful calcium carbonate home, okay? And so we'll show you the next picture. So these are some of the other studies that have been published: nervous system of fish, toxicity of harmful algal blooms, potential loss of water quality benefits provided by shellfish. So people, the biologists, are really doing a lot of experimentation to see what these impacts are. This was recently published by a woman, Nina Bednarsek, who works with Dick Feely down at the NOAA Pacific Marine Environmental Laboratory, and we're so lucky to have Dick Feely in our region. He's a world leader, and it's been an honor to work with him. And he brought Nina over as his postdoc, and she was the first to publish just recently their shell dissolution. So this is a pteropod shell right here, and so this is a photomicrograph of a pteropod that was in the California current system. And so that's really, the California current's just right off of our coast. It goes California, Oregon, Washington, and basically between Alaska and Mexico. And so you see a lot of dissolution on this shell. And so though this is really not good for the pteropod, it's also an indicator of ocean health. And so we're going to be looking at this phenomenon in our waters. So that's all been a pretty negative story. So are there any organisms that are going to benefit from ocean acidification? That's a good question. Well, if it were to be, it probably would be a photosynthetic organism, because what do photosynthesizers do? They take up CO2, and we're giving them a lot more CO2. Well, things like seagrasses and kelps, maybe they will have a better time growing, or maybe we could use their growth in floating rafts to partially mitigate the effects of water. This is all stuff that's being proposed and hasn't been studied yet. On a large scale, is it going to make a difference? No. Think of the scale of the oceans versus scales of floating rafts. But in a localized bay, could it make a difference? Maybe it could. We don't know. Some species may be able to adapt, and Gretchen Hoffman down at UC Santa Barbara and several people who do their experiments right over here at the Friday Harbor Labs are looking at that, looking at the time scale of adaptation versus the time scale of change. So, just recapping what we've been saying so far is that OA is happening, and it's happening at a rate that's nearly 10 times faster than any period over the last 50 million years. So one of the things I always say when we're thinking about ocean acidification is that it's a global condition, but its effects are very local. All right, and that's really important to understand. So here's this global condition. I showed you the data from Hawaii, the CO2 like from the air in black, and then the CO2 in yellow from the seawater. But look at Bermuda and the Canary Islands. They have the same slope for CO2, for pH, and for carbonate. So it really is a worldwide phenomenon. But look at this picture, and hopefully you recognize a few folks there. This woman, of course, is our former governor, Christine Gregoire. You may not know Bill Dewey from Taylor Shellfish, who is a shellfish farmer and part of the Taylor enterprise. And I just love this picture because it's like, look, it doesn't work the same anymore. So Governor Gregoire assembled a blue ribbon panel to summarize the scientific knowledge that was known about ocean acidification in Washington state waters, and to make recommendations from knowledge to action. So this was during 2012. And why Washington? Why are we dealing with this here? Well, there's a lot of regional factors about Washington that makes us more susceptible to this issue than other places, though all places are going to be influenced by this. So we have regional factors. One is coastal upwelling. What is upwelling but deep waters coming to the surface? Okay, we'll look at that in a little bit. Runoff of nutrients and organic carbon from land-based activities or decay of organic matter in deeper waters. And so let's put some pictures to this. So here is upwelling. That happens when you get the winds that are equatorward. So coming from the north heading south, you get, due to the Earth's rotation, you get those deep waters coming to the surface. This has been a thing that has made our region so productive. It brings nutrients up, phytoplankton grow. It's a great thing. Lots of photosynthesis, taking up the CO2. But what happens there is that, I'm going to skip that, is that photosynthesis consumes the CO2 at the surface, but then this organic material sinks, or it gets consumed, and those consumers defecate, and that organic material sinks. Okay, so you have respiration that releases CO2 near the bottom. In our Pacific coast, we make a lot of this, so therefore we've got a lot of that, and then we've got upwelling that brings it back up to the surface, all right? So we've kind of got the natural system that brings these high CO2, lower waters naturally to our system. Now, this is kind of an interesting effect, because this could say that our species are naturally adapted to low pH, high CO2, and that could be a good thing. On the converse, it could be that we're closer and closer to a threshold, so that could be a bad thing. And I don't know where we are on that curve, and a lot of that research is going on. Then if we add nutrients or add organic material, that just adds to the carbon load and adds to the respiration load, okay? Now, to back up and show you the slide I passed, this is the West Coast picture. This is the East Coast picture. What is this gray? This gray is the continental shelf, which on the West Coast is very narrow compared to the East Coast. And we have a lot of upwelling that brings this high salinity water upwards. Sorry, this is depth on this axis. This is distance from shore, okay, going out from the coast of Washington, going out into the ocean. Whereas here, this is, you're on the shore and you're going out into the Atlantic. And they don't have as much of that phenomenon known as upwelling. And so our low oxygen, low omega aragonite waters are coming upwards. That same phenomenon doesn't happen on the East Coast as much. However, we are seeing in Maine, in New England, New Hampshire, Massachusetts, we are starting to see the effects even without the upwelling, okay? But that's why Washington is especially prone to it. All right, so are local stressors contributing to? That's a very open question and important one for us to understand. Things like emissions of gases that can also contribute to the acidifying reactions, things like erosion, things like nutrient input. Are they affecting on a measurable scale how much carbon load is there? Maybe they are, maybe they aren't, and that's something we need to better understand. This is a really cool time series. So what we've got here is another measure of CO2 in the atmosphere, and this is time. And the green data are from a buoy off of the coast of Washington, Cape Elizabeth, if you know where that is. And so you see that seasonal cycle of uptake during the summer and not as much uptake during the winter, so that breathing of our biosphere. But then look at this blue series. This is the same sensor put on the Space Needle in Seattle by NOAA PMEL. And look at how these numbers are so much higher and they're very spiky. And a lot of that is from the automobile emission of CO2. And in fact, when we had the big snowstorm, you could see it just flatten. So anyway, so that's the human signal of just an urban area like Seattle. And of course, that's going into a huge reservoir the world round. We don't know whether this increase in CO2 is having an impact on our local waters. On a global scale, of course, it all contributes. But anyway, so that's another open-ended question. But I think seeing pictures like this helps us really to realize that, you know, it is our human actions that are making a difference here. So here's a lot of open-ended questions. What determines local nearshore CO2 levels? How can CO2 levels be measured easily and quickly? There's an X Prize challenge on this that's out there to develop better sensors. What management could reduce local OA? How fast and how far can species acclimate and adapt? Where are crucial tipping points? Which ecosystems are more or less resilient? So those are all really important things to investigate. And once you are in inland waters, it's much more of a challenge because of this high variability, because of the high diversity of things that are causing that variability. But because it has widespread biological effect potential that we really don't understand, it's really critical to do this. So here are some calculations that Dick Feely and others made of along the Washington, Oregon, Northern California through Southern California, how much of this acidification signal is due to this upwelling of the deep waters, how much is due to respiration, and how much is due to the global CO2 emissions. And if you look at that, the majority is this upwelling phenomenon. Respiration is important also, but this global CO2 emissions is not a trivial fraction. And as time goes by, because our trajectory for fossil fuel combustion is increasing, not staying level, this number percentage will increase. And that's important in places like Puget Sound because we get this oceanic end member water coming in across the sill. And so then anything that we do locally is only going to increase that carbon load. And so anyway, you get the picture. It's additive. And so this is from another paper by Dick and others, where if you look at the ocean acidification signal in a place like Hood Canal, it's 25 to 50% of the signal, and will definitely increase as time goes by. So here's just kind of a picture of all of the factors that can be involved when you study a marine system. And then when we start thinking about Washington's marine waters, whether we're studying Puget Sound, the outer coast, shallow estuaries, the Columbia River, they all have a different assortment of those drivers. And so what we're trying to do is get a handle on the status in Washington waters and those influencing factors that you see here. All right, so this was the governor's Blue Ribbon Panel report, and in that following legislative season, when Governor Inslee came in and the legislature acted, they established a Marine Resource Advisory Council, and Martha Consgard is the chair of that. They established the Washington OA Center at UW. As Fiona mentioned, Terry and I co-direct that. And they directed our center to implement 5 actions from the Blue Ribbon Panel report. And what are those 5 actions? To continue the monitoring at the existing shellfish hatcheries, including Mark Weigert's, including the Taylor that Bill Dewey's at. Expand and sustain ocean acidification monitoring, so across all Washington waters. Conduct laboratory studies on Washington species and ecosystems, and I'm happy to say that some of those experiments are being conducted right over there at Friday Harbor Laboratory. Make short-term forecasts of corrosive conditions. So we've got some modelers who are working to create real-time displays of the corrosive conditions in a computer format, so you can look at that and see when corrosive conditions are more, there's a higher risk of getting them or not. And then to work with growers to think about different kinds of commercial scale water treatment methods. So we're working with the Pacific Coast Shellfish Growers Association on that. So I'm going to skip over these things because we've sort of talked with them before and I was over ambitious when I put my slideshow together. But if you go to the center's website, which you'll find at the University of Washington, just Google Washington Ocean Acidification Center. The URL's way too long for me to give it to you, but you will get there. You'll see that we have sort of a Wikipedia, 6 things we know about OA in Pacific Northwest coastal waters, okay? And you'll see these explanations. And it also has links to the primary literature on which these statements are made, so you can go to the primary literature too. The thing about where we are in our current status is that we're crossing this threshold instead of 11% of the time, we're crossing it 33% of the time by this publication by Harris et al. So this is a great quote, makes a bad day worse, all right? It's not that we didn't have bad days before, but it's just, it makes it worse and we have more of them. So, we're trying to still figure out the species. Washington State's a leader in this, and it's really exciting to see other states in the Union starting to take action, and other nations, and our own nation recently was called to action by Secretary Kerry at the Our Ocean Conference to start really making some advances on this. Washington isn't alone. We work in the context of NOAA, EPA, and US IUS that Mark Weigert mentioned, and Fiona mentioned NANUS. NANUS is the regional association of the US Integrated Ocean Observing System for the Pacific Northwest. So NANUS stands for the Northwest Association of Networked Ocean Observing Systems. And so here's another great quote by Mark. He just is so amazing with his quotes, like, yeah, ocean acidification, what scientists call it, the larvae hated it. You know, they died. Putting a buoy in the water is like putting headlights on a car. You know, so no scientist would come up with that, but it's exactly what we're striving to do, is let people see the water conditions in real time. So NOAA is also making some technology investments, working to get the monitoring equipment not only in Oregon and Washington, but up and down our coast. And then here's our NANUS visualization system. So if you just go to www.nanus.org, you can find all of the data. And once you discover it here, it's also discoverable on the national system. And then the national system feeds into this global system. And that's something that I think is really worth doing, because if we're going to get our global assessment correct, you know, I said OA is a global condition with local effects. You can't understand the local effects unless you understand the global context it's in. But also, we can't understand our global condition unless we get that mosaic of local situations, right? So it's really been fun to work on all of these scales, and it's critical that we have strong coordination back and forth among those scales. So that's a big role of the center, is to be that coordinating body that tries to bring a regional focus and to get the science connected with the managers and policymakers to promote outreach and education and to engage broadly. And we're really exciting. I said one of those actions we want to implement was the monitoring network. Look at all of our partners to date. Oops, and I'm really happy to say Olympic National Park, you're going to have Steve Fradkin here as one of your speakers. He's going to be part of our monitoring system with some new sensors that we're going to equip him with to make side-by-side measurements with what he's been making for years. So it's really exciting to see everybody step up. Obviously, Friday Harbor Labs is a big part of this. Shannon Point Marine Center, Western Washington University, tribes, etc. So, but now instead of everybody doing their own thing, we're bringing it together through the center. And you'll be able to see the data over NANUS. Really cool research on cruises in the intertidal, buoys that are going in Puget Sound, teams of students and technicians working on these. And I wanted to give a shout out to Friday Harbor, my home away from home where I teach every fall, and to say that they've got a wonderful OA environmental laboratory there where lots of analyses and microcosms and mesocosms are going on. And through my students, we have started a time series that Connie Sullivan defended for her master's years ago that I just presented at the Salish Sea. And it takes advantage of these two stations, which we've been monitoring since 2004. And it's really interesting because you've got a river, Fraser River, and an oceanic driver, and these are really good end-member systems. So with students, we've been going out to those stations on the Centennial. Some of you have even helped. Phil's here, has done a lot of these cruises, measuring all of these things, including the OA variables. There's Connie. She's just been hired as the OA-EL lab manager. She'll be moving up here in July to do all of these measurements and then to continue the data series, which we're doing with our partner through Western, Jude Apple, and to sustain these measurements year-round. So we're getting good measurements in your area to better understand it. So I'm going to end with this slide, and sorry I've talked a little long because I really am interested in your questions. But I wanted to give you a flavor of how it's really critical that we're looking at the local through the global scales. And I think it's also really critical that we're working in a coordinated fashion because, you know, this is a big issue here. And it takes people like yourselves who want to understand the underlying science, who want to understand it, to take it into your lives and think about, you know, where we can go as a planet. So anyways, I love the oceans, and I know you must too because you wouldn't be here, and I just thank you for your attention. I look forward to your questions. That's all. Thank you. Questions?